Welcome back again. So we are doing the last section of Unit 3 today. It is still Math with Business Applications. I guess I should probably come up with a better intro than this, huh? Okay. Sorry, I got pizza in my teeth. All right, let's see if I can figure this out. Hi, this is Math with Business Applications. I'm Amy Fuchsteiner, your instructor for this course, and today we're going to work on the last section of Unit 3. This is going to be about the normal curve and the empirical rule. So we're going to take a look at normal curve and the empirical rule. This is in your supplement in part 10. For those of you who may need a reminder, the supplement can be found under the course syllabus and schedule on Blackboard under your Math with Business Applications course. All right, so our goals for this particular presentation are as follows. The first thing we want to be able to do is we want you to be able to recognize characteristics of a normal curve. We want to talk about what an outlier is and where we find them. Then we're going to introduce the empirical rule. And we're going to have you explain that and work with it. So we're going to use that empirical rule to answer some questions about our data. We're going to use it to help us determine the percent of a certain range of data. We're going to use the empirical rule to determine the amount of data within a specific range, and we're going to determine the range for a specific percentage of data. So to begin, we're going to start with the characteristics of a normal curve. A normal curve is also known as a bell curve. And we're going to go through some of the characteristics of what are known as normal distributions in terms of the histogram. So we start with the idea that a normal curve is bell-shaped, that it looks like an upside-down bell. This is a histogram with a normal distribution laid over the top of it. Notice that it comes up along the side, it has a definite peak, and it goes down the other side. So it's almost like a slide, right? You climb up and you go down. Great. Now, in a normal curve, the mean, the median, and the mode in a perfect normal curve are all the exact same number and occur at the peak, the very top of this bell. In real life, they're not always exactly the same, but they are very close, and they do still occur near the peak or top. This presents symmetrically in most normal curves. Well, in all normal curves, it has to be symmetrical. That is, once you know the middle, the left side and the right side, everything to the left of the mean and everything to the right of the mean, mirror each other. Normal curves are known as density curves in that everything underneath the curve is considered to be 100% of the data and therefore has an area of 1. The mean would be halfway. Since it is centering, the area above that mean, that is to, well, let's see, I can do my left to rights. That is to your left? No, that's right. Everything to the right of the mean is considered above, and that would be 50% because the mean is at half. It's 50% of the data. Everything to the left of the mean would be half below the mean. That would be the 50% of the data below the mean. Probability of choosing a point in the bottom half is 0.5. The probability of choosing a data point in the upper half is 0.5. So probability of choosing a data point in either area is 1/2. Little piece here that's kind of important. The curve itself for the bell curve or the normal curve is often drawn to be touching the horizontal line, but it is not meant to. Because with a normal curve, it's 100% of the data, we need to leave a little bit of a room to keep adding more data to our set. That means that we never close down the data and have it touch at the bottom. So here we have a little NOMI guy, and he could go anywhere. As long as he can get in underneath that curve, he can go ahead and move in and be placed appropriately within the histogram bars. So there comes my third one. Here's my little Nomi guy. Here we go. All right. Seventh characteristic. It has to follow what's known as the empirical rule. The empirical rule is stated for normally distributed data that 68% of the data will be within one standard deviation of the mean. That is to say, if the mean is the center, then 34% would be one standard deviation above the mean, and 34% would be one standard deviation below the mean. This gives us a range of 68% of the data within one standard deviation of the mean. That's one above and one below. Now, part of this comes from the idea that standard deviation is the class width in a normal curve. We talked about that a little bit last presentation. So that means that our standard deviation can go one class width above and one class width below. And if there were 100 pieces of data, 68 of them would fall within that range. That is one standard deviation above and one standard deviation below. The second standard deviation, if we were to go 2 standard deviations out, that would contain, 95% of all of our data. So if we had 100 points, 95 of them would be within 2 standard deviations of the mean. And the third part of the empirical rule says that 99.7, not 100, because if it were 100, we could close it down, but we can't close it down. So 99.7% of all data is within 3 standard deviations of the mean. That is 3 standard deviations above and 3 standard deviations below. You will notice that this means that there is not much data at all outside of 3 standard deviations. There is 0.3% or 99.7 taken from 100, leaves us with just 0.3% of all data outside of 3 standard deviations. The data that falls outside of 3 standard deviations is known as an outlier. Now, second thing we want to be able to do is to understand what an outlier is. An outlier is defined as a data point that will differ significantly from all other observable data. We have here a quote from Malcolm Gladwell. It says, "The lesson here is very simple, but it is striking how often it is overlooked. We are so caught up in the myth of the best and brightest and the self-made that we think outliers spring naturally from our Earth. We look at the young Bill Gates and marvel that our world allowed that 13-year-old to become a fabulously successful entrepreneur. But this is the wrong lesson. Our world only allowed one 13-year-old with unlimited access to time-sharing terminal in 1968. If 1 million teenagers had been given that same opportunity, how many more Microsofts would we have today?" So traditionally, the idea of an outlier is the one piece of information that proves your pattern doesn't exist. It is the one piece of information that bucks all of the rules and proves that everything you thought was right is turned upside down. In other words, your theory is wrong. Now, we see this in the real world when we talk about a gentleman by the name of Muggsy Bogues. Now, Muggsy Bogues, let me get my notes. Muggsy Bogues was a 5-foot, 3-inch point guard for the Carolina Hornets. He spent 14 years in the NBA, 10 of them with the Hornets. Now, I don't know a lot about basketball, but if you look at this picture, you can see a picture of Muggsy Bogues. Muggsy Bogues is shorter. He barely comes up to the word Charlotte on the 2 other basketball players there. Muggsy Bogues is 5'3" and made it in the NBA for 14 years as a basketball player. He is an outlier. You can see an outlier on a histogram by looking at the data point that is outside of all the rest, the same as we can on this line graph where it says your theory is wrong. Now, outliers are not just statistical anomalies. Outliers are things that we aspire to be, much like Muggsy Bogues, much like Bill Gates, and probably you have someone who has done something amazing either in your life, within your life, or perhaps someone that you look up to. And they are probably in some way an outlier. Now, because I love to read, I'm going to recommend Maxim Gladwell's book called Outliers. Basically, his whole premise is, one of his premises of this book is that it takes 10,000 hours. If you want to be an expert at something, you need 10,000 hours. It's a great book, really. Give it a shot. All right, back to the actual outlier bit of it. So on a visual, on a histogram, we can recognize an outlier because you can see where the pattern is and sort of where the normal curve is. And then we've got this one piece of data that's sitting out on the far right. That's an outlier. Outliers are fairly easily recognizable in the data when you're looking at it all together. But there is a mathematical flow to how you find it. So here's some questions to ask yourself. Is that data point above the mean or below it? If it's above the mean, then you want to do 3 times the standard deviation and add that to your mean, because we know that the outlier has to be outside of 3 standard deviations. So if I know a standard deviation is 10, then I know that outlier has to be 3 times that, or 30 plus whatever the mean was. If that data point is still higher, then you have an outlier. If it is not, then it's not an outlier. Similarly, if that data point is below the mean, then you subtract 3 times the standard deviation. If that data point is still less, then it is an outlier. If not, then it's not an outlier. So here we have some outliers. In 1980, the average age of a mother at first birth, so the first child that they had, was 22. The curve was approximately normal with a standard deviation of 3.3 years. So where would the outliers be? So the outliers would be outside of 3 standard deviations above the mean. Since the mean is 22, oh, looks like I switched my number. Hold on. Let me grab this. No. You need to alter pen 24. Okay, we're going to try 24. I apparently switched it. All right, so if the average age of a mother at first birth was 24, the curve was approximately normal, 3.3. So I'm going to take that 24 and I'm going to add 3 standard deviations to it, or 3 times 3.3. That gives me 24 plus the 9.9, which is 33.9. So that means that anyone who is age 34 or above having a baby, their first baby, in 1980 would have been considered an outlier. Similarly, 3 standard deviations below the mean, or 24 minus 9.9, would have also been an outlier. So if someone had a baby, their first baby, before they turned 14, that also would have been considered an outlier in terms of data. By 2016, the average age of a mother at first birth was now 29. Did I keep that? Yes. The standard deviation has also increased to 4.8 years. So basically, the age of first birth had moved up significantly, and the spread, or the amount of diversity within that particular data set, had also increased. So our standard deviation, 3 standard deviations above the mean, would have been 29 plus 3 times 4.8, or 29 plus 14.6, or 43.6. And now, if you are nearly 44 having your first baby, that would have been considered an outlier. 3 standard deviations below the mean would have been 29 minus 14.6, or 14.44. Notice we're still able to keep the lower outlier fairly the same, and that has to do more with actual biologicals than it does patterns and habits of people, I think. I'm speculating, maybe not. All right, so hopefully from that you have an idea of what an outlier is and a couple of different ways of how to determine whether or not you have one. Lastly, today we're going to look at the empirical rule, and we're going to do some things with it. So here I have a diagram of the normal curve broken down into the different sections for the empirical rule. The empirical rule provides a quick estimate of the spread of data in a normal distribution where the mean and standard deviation are known to you. The empirical rule is going to be used to determine what percent of a population falls within data, the probability of any given data point, the number of data points within a given range, and the range when given a certain number of parameters. As a quick aside, you can also use the parameters of the empirical rule to determine whether or not there's a possibility that your data is normal. For example, stupid little ones. For example, if I knew that 75% of my data, I did a quick count and I found that 75 or 80% of the data was within one standard deviation of the mean, that would indicate to me that it's probably not normal. The same as if I did a quick calculation and found that only 20% of the data was within one standard deviation of my actual mean, that would tell me that it's probably not normal. Because in order to be a normal distribution, I need about 68% of the data to be within one standard deviation of the mean. It's also useful to note that these little sections here, this section here and this section here have to be 0.15%. How am I getting that number? I'm getting that number because I know 3 standard deviations is 99.7%. So as I stated earlier, 0.3% is going to be outside of that standard deviation, those 3 standard deviations where the outliers are. But here's the thing, because of the symmetry, half of those will be above and half of those will be below. So if I take 0.3 and divide it by 2, I get 0.15%. Now, as we do this, here's my recommendation. You see this lovely little colored chart with the purple, the green, the gold, and the 0.15s on the outside? Keep this near you for reference. This, with the percentages and the references, is what you're going to need for 68%, 95%, 99.7%. This set of, 11 numbers, this set of 11 numbers on this diagram is going to be extraordinarily helpful as we work through the rest of this section. All right, 20 minutes in, great. Okay, so here we go. Some problems using the empirical rule. With this first example, we're going to go ahead and determine percents. So the scores of 3,452 high school student seniors taking the verbal section of the Scholastic Aptitude Test, SATs, in a particular year had a mean of 490 and a standard deviation of 100. The distribution of SAT scores is considered to be normal. So the first step we're going to do here is we're going to place the mean and the scores on this normal curve at the right. So to begin, the mean goes in the middle. This is our 0. So at 0, I'm going to put 490. Notice the 0 is in the middle. And I like to draw a line directly above to the 490. Some people prefer it below. There's a little bit in this. Now, the standard deviation on this guy is 100. So if I go 1 standard deviation above the mean, that would be 490 plus 100, or 590. If I go 2 standard deviations above the mean, that's another 100 up, or 690. And if I go 3 standard deviations above the mean, that would be 3 times 100 plus 490, or 790. Thus, I have all of the standard deviations marked above the mean. For the standard deviations below the mean, I'm not going to be adding 100, I'm going to be subtracting it. So 490 minus 100 is 390. And if I subtract another 100, I have my second standard deviation below the mean, and another 100 to get my third standard deviation above the mean. And thus, I have placed all the scores on my normal curve here. Why did I do this? Well, because now I can answer the questions that were asked. What percentage of students score from 390 to 590? So using a highlighter, I'm going to find 390 and I'm going to color or shade in over to 590. You can see the part of the normal curve that's shaded in is from -1 to 1, or 1 standard deviation below to 1 standard deviation above. Using my empirical rule, I know that this has to be 68% of all of my data. So what percentage of students scored from 390 to 590? They're within 1 standard deviation of the mean, so that's 68%. Second question, what percentage of students scored from 290 to 690? Well, using a highlighter in red this time, I'm going to start at 290 and go up to 690. And I'm going to shade in everything underneath the curve. When I do that, I see that I'm going from a -2 to a +2, or from 2 standard deviations below the mean to 2 standard deviations above the mean. Referencing my empirical rule, I know that this has to be 95% of all data points. So what percentage of students scored from 290 to 690? 95%. Question 3. What percentage of students scored less than 590? Well, for less than 590, I'm going to start at 590 and I'm going to follow the curve all the way down. So when I do that, you see how I'm going past the -3? Because I want to go everything to the left from the 590. You'll notice this encompasses the whole lower 50% and then the first standard deviation above. So the lower half is 50%, everything from 490 down is 50%, and then referencing my empirical rule chart, I see that the first standard deviation above is another 34%. Adding those together, I have 50% plus 34%, which is 84%. All right, next question. What percentage of students scored more than 690? Well, this one is more than 690, so I'm going to start at 690, using pink this time. I'm going to start at 690, and the more than indicates everything to the right. So starting at 690, I'm going to shade in everything to the right. Now, if you look at your reference again, the empirical rule chart, where we go? Here we go. You can see that this, from the second to third standard deviation, is 2.35%. And everything outside of 3 standard deviations is 0.15%. Since my pink has shaded those two sections, I'm going to add those two together, 0.15 times 2.35, to get 2.5%. So what percentage of students would have scored more than 690? That's the 2.5%. All right, let me erase this now because now I got the next one going. There we go, erasing. Okay, what percentage of students would have scored less than 190 or greater than 790? So this is two options at the same time, less than 190 or greater than 790. So I need to do both of those. So in blue this time, I'm going to find 190 and go less than that. And I'm also going to find 790 and go more than that. Do you notice that these are both the 0.15s? So if I reference the empirical rule chart from the previous slide, I get 0.15 here and 0.15% here, outside of 3 standard deviations. So what percentage scored less than 190 or greater? That's 0.15 on each, or 0.3%. All right, great. Now, same idea, a little bit different question, but we're going to start the process off the same way, always beginning at the same place. So determining the numbers this time. A manufacturer of lithium-ion batteries has found that the life of their battery follows a normal curve with a mean of 32 months and a standard deviation of 4 months. So their batteries on average last for 32 months, but there is a standard deviation of 4 months. 2,000 batteries have been purchased by a distributor. First things first, we're going to place the mean and the scores on the normal curve. So the mean and the data points on that normal curve. So putting the -3 to 3 across the bottom and finding the center and placing the mean there. So at the center, we have a mean of 32. With a standard deviation of 4 months, if I go one standard deviation above, I am at 36. A standard deviation above that would be 36 plus 4 or 40. And the third standard deviation would be another 4 added on or 44. Standard deviation lower or to the left, I'm going to do 32 minus 4 to give me 28. 28 minus 4 is 24, and then 24 minus 4 is 20. And so now at this point, I have labeled the normal curve with the standard deviations along the horizontal and placing the actual data points or data references across the top of the curve. So, question number 2. How many batteries will last less than 32 months? So using yellow, I'm going to find my 32, and I'm going to highlight everything less, that is everything to the left. Being sure to go beyond 3 standard deviations because I want to include even the numbers that are below 20. When you look at this, you see that you have 32 and everything to the left. This is half of our data, so this would be 50% of the 2,000 data points, or 0.5 times 2,000, which is 1,000 batteries. We would expect 1,000 batteries will last less than 32 months. How many batteries would last between 28 and 36 months? Well, using blue this time, I'm going to start at 28 and highlight over to 36. Looking at what I've highlighted in, I see this is from 1 standard deviation below to 1 standard deviation above. I know, referencing my empirical rule, that that needs to be 68% of the data, or 68% of my 2,000 batteries, which is 0.68 times 2,000, or 1,360 batteries. How many batteries will last between 20 and 40 months? So starting at 20, I'm going to go all the way up to 40, and I'm going to shade all of this in. This one's a little bit rougher because what I have here is from -3 to a +2. So when I reference these, you can build this a couple of different ways. If you're referencing the empirical rule and the colored chart that was on that other slide, we've got a 2.35. From -2 to 1 is 13.5. This one is 34. And then the symmetry means this would be 34. This would be 13.5. So now I just need to add up all of these sections. So 2.35, 13.5, 34, 34, and 13.5. That's one way to do this. If I add all of those together, we will get the 97.35, or 97.35% is how much data is there. And since we have 2,000 batteries, we're going to have 93.75 of 2,000, which is 1,947 batteries. Now, some of you may say, okay, Amy, but can't I just do, hey, these 2 standard deviations from -2 to 2, that's got to be 95%? Yeah, but then you still got to add the 2.35, which is still going to give you 97.35. There is more than one way to build to this 97.35. In fact, some people even prefer to subtract, but I don't know if you want to go there. If you're a subtractor, good for you, but I don't feel like we have to go that route. I prefer to look at the pieces and add them together, or to look at my 68, 95, 99.7 and build off of that. All right, so I need to erase my little notes here. Erasing. Here we go. All right, there we are. And then question 5 says, how many batteries will last more than 40 months? So I'm going to go 40 and up. Notice again, this is from the second standard deviation up. I would do a 2.35 plus a 0.15 to get 2.5% of 2,000, or 0.025 times 2,000, which is going to give me 50 batteries. Last question on this particular slide, how many batteries will last less than 24 months or more than 36? So less than 24 is 24 and to the left. And then more than 36 is from 36 and then up to the right. So I'm again going to add those up. I know that, where's my pen? I know that this bit on the outside, where are we? Oh, here we are. This is 0.15%. This is 2.35. And then I've got the same over here, 0.15 hanging out, very little hanging out there. That's why that's where the outliers live, very little there. And 2.35. And then this is 13.5. As a reminder, I am not getting these numbers from nowhere. I am pulling them off the empirical rule reference, the one that has it broken down into different categories. All right, if I add all of those percentages up, I am at 18.5%. 18.5% of that 2,000 gets me 0.185 times 2,000, or 370 batteries. Okay. What's the third one here? The third one was determining range. And I think I actually have 2 slides on this just because it took some more to write. So an archaeologist uses tree rings to date the settlements of first peoples. In one settlement, the samples resemble a normal curve with a mean of 1350, that's the year, 1,350, and a standard deviation of 36 years. First thing we want to do is place the mean and the scores on the normal curve here at the right. So we're going to put the -3 to 3. This is the standard deviations away from the mean. Notice that 0 is the mean. I'm going to place the 1350 at the 0, and then I'm going to add 36 years for each standard deviation. So at 1 standard deviation above, I will be at 1386. At 2 standard deviations, I'll be at 1422, and at 3 standard deviations, I'll be at 1458. For the standard deviations to the left, I need to subtract the standard deviation of 36. So 1350 minus 36 is 1314. Taking another 36 away, I get 1278. And taking another 36 away, I get 1242. So they want you to estimate the range of years centered about the mean, which 68% of the data was found. So what you have to recognize here is that 68% is an important number for the empirical rule. The 68% is within 1 standard deviation of the mean. That is 1 standard deviation above and 1 standard deviation below. That means that I can look at these numbers of 1314 and 1386, and those would be the range of years in which 68% of the data is found. All right, similarly, erasing. Similarly, we want to estimate the range of years centered about the mean for which 95% of the data was found. We're asking you again to recognize that the 95% in terms of the empirical rule means 2 standard deviations below and 2 standard deviations above. And if I look at the dates that encompass those 2 standard deviations, we're going from 1278 to 1422. So our range of years would be from 1278 to 1422. Third question. Estimate the range of years, again with the center at the mean, in which 99.7% of the data is found. So for our 99.7, we're asking you to recognize that for the normal curve and the empirical rule, 99.7 is 3 standard deviations above and 3 standard deviations below. This goes from 1242 to 1458. All right, moving along. Our next slide is the same again. Same set of data, just a little bit different questions. The first question says, estimate the range of years for the upper 50% of data. Well, the upper 50% of data is going to start at the mean, which is 1350, and it's going to keep going past 3 standard deviations. So we want to start at 1350, but we don't want to give it a closing date because it's just the upper 50%. And remember, we said that the normal curve doesn't close. It just sort of floats above the number line there. So since it doesn't close, we would simply say 1350 and above, or 1350 and later in terms of years. What if we had to find the lower 97.5% of the data? Well, this one's a little bit trickier because at lower 97.5%, we're asking you to leave out the top 2.5%. So do you recognize that top 2.5% would be everything? Because remember, this is 2.35 and this is 0.15. And if I put those two together, that's 2.5. I want the lower 97.5%. So I want everything from 1422 down. That means 1422 and below, or 1422 and before, if we're talking about it in terms of time. The range of the upper 16% of the data. Erasing, erasing, erasing. There we go. The upper 16% of the data. So the upper 16%, oh, we knew this was 2.5 and this is 13.5. Whoops, this guy is 2.5 here. This one and this one together. Let me get my pen again. So if we're looking at the upper, we're looking at this side. Recall that this is 34. Between 1 and 2 above is 13.5. Between 2 and 3 is 2.35%. And above 3 is 0.15%. I need the upper 16% of the data. So starting at the top, if I add them up, I get 0.15 plus the 2.35 plus the 13.5. These three together are the upper 16%. So I just need everything from the 1386 and above. So I need the upper 16% of the data, which would include 1386 and above. All right, what do we got going on next? So that's sort of it for today. Can you do the following? After this presentation, can you recognize characteristics of a normal curve? If I asked you for 4, 5, or 6, could you list them? Right? Could you define an outlier in terms of its actual definition, but would you recognize it when you saw it? Could you, if given a piece of data, could you figure out whether or not it's an outlier based on the mean and the standard deviation? Could you introduce the empirical rule to somebody else and explain it? And can you use the empirical rule to answer some questions about data? Can you determine the percent of data in a specific range? Can you determine the number of data points that would be within a range? Can you determine the range if given a percent? All right, so practice I am actually going to not recommend you do the supplement part 10. I am going to include a worksheet. I'll put it in the worksheet. Aha. I'm going to put a practice worksheet in the file for you guys because I feel like that might be a little bit better fit with this. I'll have the blank worksheet and the answer key there so that you can practice this a little bit more if you want to. There is an assignment. The assignment, yep, this graded assignment is on Blackboard. It is called Empirical Rule and Normal Curve, and it does go through much of what we did here in the presentation today. If you have any questions, please do not hesitate to reach out to your instructor, to your math support personnel, or to pop into the Math Center for assistance. Again, we are all here to help, and we want you to do well. Thank you.